Do you guys see that? These things are just falling at basically terminal velocity as they were coming across the screen. It's almost like that's the topic that we're going to learn about today in this video. That's amazing. Well, in any case, here we go. We are, in fact, going to learn about drag forces today. One important part of that being the phenomenon of terminal velocity that I'm sure you've heard of. Now, one thing I want to make very clear from the beginning when we're talking about terminal velocity and the general idea of drag forces is this. Things have a maximum speed when they are falling, not because gravity gets tired, but because there is another force which prevents them from going any faster. And that force is called a drag force. Drag forces in general are forces that depend on the velocity of the object in question. And they apply when it's moving through any kind of a fluid, which in physics is both gases and liquids. So these equations that we're going to derive apply equally to things like air resistance, but also sinking through a vat of maple syrup. Okay. Or in theory, they could even apply to something like a beach ball rising because of buoyant forces as it moves upwards through, like a pool or something, right? If you get a beach ball all the way down to the bottom. Anytime anything moves through a medium, which is a fluid, however you want to define that, all right, gases or liquids, drag forces are going to apply. All right. In most cases, the problems that you guys are going to do are going to be with first order drag. First order drag forces follow an equation that looks like this. Okay. Second order drag, it's a squared. Okay, so that name should make sense to you, right? First order means it's a linear function, second order means it's not. Most of the time in real life, this is what most drag forces actually look like, but the math is actually way more complicated to deal with when it's second order drag, and so for the purposes of making it possible for you to do the questions, a lot of them are going to be first order. Okay, so I wanted to work through one example question, which is going to be pretty typical of the kinds of drag force problems that you guys are going to have, just so you can see how most of them are going to get set up, or at least how you ought to approach setting up a drag force question. All right, so it says we've got an object of mass m falling with air resistance, assuming there's a first order drag force and then all this stuff. All right, so to start with, they want us to draw a force diagram. Well, all right, if we have something that is falling, there's obviously gravity acting on it. Whoa. Okay. Now, at the moment that you release something, whatever it may happen to be, the only force that's really acting on it is gravity, pretty much, right? So, even this coffee filter, at the moment I let go of it, gravity's the only thing acting on it. But after it's moving a little bit, there's going to be this drag force that acts on it as well. All right, now the thing about terminal velocity is that at terminal velocity, the force of gravity pulling down and the drag force opposing it are equal. When those two forces are equal, well, the sum of the forces is 0, and so since the sum of the forces equals ma, if they all add up to 0, that means the acceleration is 0. So at terminal velocity, the acceleration is 0. All right, that's a pretty crucial fact right there. All right, so anytime they say calculate the terminal velocity, you're going to see in the course of this video a lot of scary differential equations that resolve and get solved and everything. But you're also going to see some simple stuff that happens. And one of those simple things is finding terminal velocity. You don't need to solve a differential equation to find out what the terminal velocity is. There's going to be a much simpler way that comes back to this fact right here. Okay, now what does that have to do with our force diagram? Well, it says draw a force diagram before terminal velocity is reached. I didn't write is reached, but that's okay. Well, I'm going to draw this. Do you see how this arrow is longer than that one? All right, so what you guys ought to remember from, vectors and such is the length of the vector tells you the magnitude of the whatever kind of vector it is. So if these are force vectors, well, that one is a smaller force, which is why it's continuing to accelerate downwards. Please note, not move downwards, right? It will move downwards even at terminal velocity, but it won't be accelerating anymore, right? So it's still accelerating when it hasn't yet reached terminal velocity. All right, part B wants us to draw the force diagram when it's at terminal velocity. So if it's at terminal velocity, be very careful to draw two arrows of equal length. And if you're not sure that your diagram looks good enough, then you could actually go ahead and point out, hey, those are equal length. All right, so there it is. So if you're at terminal velocity, those two forces are equal. All right, now the next question. It says VT. That's my abbreviation for terminal velocity. They would say, in the text, the words terminal velocity. They're not going to abbreviate it for you. But if they say, what is terminal velocity? You're like, gosh, I'm going to have to do a differential equation. We will do the differential equations later. We can solve for the terminal velocity without doing any really fancy math, right? So let's do this. We'll write an equation for the sum of the forces. All right, so here's the most common equation that you're going to write for the sum of the forces. Gravity is opposed by the drag force, and at any particular moment we can say that the sum of the forces adds up to ma. All right, that works. All right, now in order to actually solve for the terminal velocity, though, we need to make one simplification here, and that is that the acceleration is 0 at terminal velocity. All right, and so now we can go ahead and move the mg over and divide by b, and we're going to get mg over b. And that's our terminal velocity, assuming that we've got a first-order drag function. All right, now, the next part, write a differential equation for v as a function of t. All right, that right there might sound extra scary. That's not the scary step. This one's the scary step where it says solve this equation. All right, I say scary. It's not, okay? At the end of the day, you will have done, well, not at the end of the day, at the end of this unit, you will have done so many of this and this that you will know exactly what to do. You won't have any hesitation about how to solve a differential equation because you will have done it so many times, okay? So the first couple of times, it's maybe a little bit bewildering, okay? And you might have to look back and forth between the notes that you should be taking while you are watching this video and your paper where you are working your problem out and see, all right, what did I do? Did I skip a step or whatever? So you may have to go back and forth a few times like that. But eventually, if you are staying on top of your homework, you should know exactly how to do these without any kind of hesitation. Even if you're not in Calc 2 right now, you will know how to do it. All right, so to start with, when they say the word differential, a differential is anything that looks like dy dx, or dx dt, or d something d anything else, right? That's a differential. In our equation that we wrote up here for weight and drag force and then ma, if what we wanted was an equation that would tell us the speed of the object at any time at all, like we could just plug in any time, 2 seconds, 0.5 seconds, and know how fast is it moving at that moment, what we would need is an equation that's in terms of time, not in terms of this other stuff. So what we have to do is express one of these things in here as a differential with respect to time in order to turn this into an equation that's in terms of time. The thing that we're going to attack is the a. Acceleration is the derivative of velocity. So a can be replaced with dv dt. All right, so then this will go like mg minus bv equals m dv dt. And now we are done with part D. That's literally everything they want you to do for part D. So if they just say write a differential equation, no problem, we just did it. It's a differential, right? It has a differential in it, and it's an equation, so it's a differential equation. If I, on the other hand, want to solve that equation for v, now we have a few more steps in front of us. Okay, so that's our next thing, and that is actually going to be the subject of the next video. How do I solve this equation for v? How do I get it to be v in terms of t? It's going to be some differential calculus. Specifically, we're going to have to integrate. All right, so that's what you'll see how to do in the very next video. Thank you.